Okay, once again, I welcome you all of you the lecture series of the Microprocessor and Microcontrollers. You know that in the past six classes, we are spending more time on this CPU, nothing but the basic structure of the microprocessor. The way we are approaching is very simple. So when you completed the all the things that is present in this structure, then only you can understand, can easily understand the entire architecture of the microprocessor. Okay, this is very much essential for you to understand each and every block that is present in this CPU at the same time. This buses and input output device as well as interface. Then only you can easily understand the total architecture of the microprocessor, how this microprocessor is worked and all. Okay, so that's why we are spending out of most of the classes, nothing but six classes. Now today also we are spending this one. So today we are going to discuss this memory as well as this interface. Okay. So today our topic is memory segmentation of 8086 microprocessor in description of the 8086 microprocessor. Okay. As you know that this is a basic structure of the microprocessor. It is CPU as well as this is some bus structure as well as memory as well as input output dividers. Memory is divided into RAM and ROM. Equally divided into the RAM and ROM. Remember, equally divided into the RAM and ROM. 1 MB. So total memory size is 2420 is equal to the 1 MB memory. This 1 MB memory is equally divided into the RAM and ROM. So this is interfacing. Interface means here pins. How many number of pins in our microprocessor? 40 pins microprocessor. Our microprocessor is a 40 pin microprocessor. Okay. So you know that different types of registers are there. So general purpose registers, segment registers, and pointer and index registers as well as flag register. Okay, flag registers. So this is the physical memory, nothing but address. This is a physical address. So physical address means a segment address plus offset address. So this is a 6-bit address. Again, this is also 6-bit address. This entirely is the 20-bit address. This entirely is the 20-bit address. How this is formed? How this is formed? You can move the 4-bit positions towards this direction. Now see this. So in the last class we are already calculated this one also. The 4-bit positions left to this one, this side. Then you can add this. This two will get this 20-bit addresses. Okay. So now see this. Our memory is total. 1 MB memory is divided into the segments. Total 1 MB memory is divided into the segments. 1 MB. So how many segments you are divided into the 16 segments, 16 logical segments. Why it is only 16? Why it is only 16? Because our register sizes are the 16 bit only. You know that a segment register size is of 16 bits. So that's why you can divide into the 16 segments. Let's see this 16 segments and so on. 16 segments. So what is the each segment size? The each segment size is 64 KB. Each segment size is 64 KB. So 64 into 16 is equal to the 1 MB size. 64 into the 16 segments is equal to the 1 MB memory. Total entire memory is 1 MB. Why it is only 64 KB? Why it is only 64 KB? Why this segment address only the 16? What is the 16? Because each register is contain only 16 bits. Now see this 16 bit segment registers. You know that what are the segment registers here? CS, code segment registers, data segment registers, extra segment registers, stack segment registers. Each of 16 bit only. Each of 16 bit only. So that's why we are dividing into the 16 logical segments. Okay, that size is 0, 0. That means here 0. This F means here 15. So total is equal to 16. So 0 is also the one number in microprocessor. So total 16. So this is the segments. This is the segment. addresses. Segment addresses. What is the offset address? What is the offset? This is the offset address. This is the 0. This is the 64 KB. This is the 64 KB. 4F H will indicate the hexadecimal. You cannot confuse that one. H will indicate the hexadecimal. Hexadecimal. H will indicate the hexadecimal. So microprocessor is under is taken the hexadecimal format data only. So that's why you can indicate the H. So this is 64 KB memory. So the 1 MB means here 5 zeros. 1 MB memory starts at the 0000 uh, 50 heads to the 5 Fs. 1, 2, 3, 4, 5. This is the 1 MB. 5 Fs is nothing but 1 MB. This is the 0 to the 1 MB memory. 0 to the 1 MB memory. So this entire 1 MB memory is divided into the 16 logical segments. 16 segments. 16 segments is here. 4 code segments. Okay. 4 data segments. Then 4 extra segments. Then 4 stack segments. Each of 4, 8, 12, 16. 16. Total you have 16 segments are there. How to identify these segments? These segments can be identified by this code segment register, data segment register. Okay, remember these are the segments. You can call it as a code segments, data segments. You can the memory you can call it as a code segments, data segments, extra segments, as well as stack segments. You can identify this segment memory. We can use the code segment register, data segment register, extra segment register, stack segment register. So that is the purpose of these registers. You can identify the segment addresses memory. You can use these 4 registers, each of 16 bit. Okay, that is use of these registers. So this code segment register will identify the code segment memory. This data segment register will identify the data segment memory. This extra segment register will identify the extra segmented memory. This stack segment register will identify the will dedicated to identify the stack segment memory. Okay. 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 So what is this? Yes. Now see this. This is the physical memory. This is physical memory. How many? What is the size of this physical memory? 1 MB. 1 MB. So what is our physical address? See this. What is the physical address? A physical address is equal to the segment address plus offset address. This is the 20-bit address. Okay, this is the 16-bit. This is the 16. So this is our important. This is the main thing. What is the 16-bit segment addresses? Segment addresses. So before going to that, so in the last class we gave you the one best example for this one. I already given that one. So whenever a person is coming to the college, first of all you go to the administrative section to identify. Then come to the department. Okay. Then come to the classes. And finally, he can identify you. He can identify you. This way, whenever you are going to identify the one person, an unknown person is or your uncle is coming to the college, so he doesn't know which branch you are studying at, he doesn't know which class you are studying. First of all, you straightly go to the administrative section or office. Office. Administrative section, you can call it as a code segments. Code segments. A course. Microprocessor, you write the programming in human level language, or add or subtract like this. You know that this is the copy instruction, this is the addition instruction, this is the subtraction instruction, this is the multiplication instruction, this is the divisible instruction. But and microprocessor doesn't know this language, and assembler is converted this language into the codes 1001 like that codes. So the codes, all the codes, this mnemonic codes, remember these we can call it as a mnemonic. All these mnemonic codes are available in this code segments. In this code segments. Likewise, which class or which branch you are studying, like that information. So which instruction it is, all the information, the codes are available in this segments. Remaining two, what are the remaining two? Then extra segments and the data segments are your information, are like the data, another but your department are like that. Okay, this two will indicate this two, good information. So next one, stack. You know that a stack is very different concept here. First in, first out case. So one stack is very different case. First in, first out case is like we are using the stack memory. So that is different case. Okay, or otherwise we have the 100 houses. We have the 100 houses. House one, then house two, then house three, then house four. We have different so on 100 houses. 100 houses. Out of this 100, we are staying at the 60th house. A person coming to you here, house one, to identify up to the he can follow the 59 houses and 60th house to identify. Okay, for suppose and 100 houses are there like this. Okay, 100 houses are there like this. So you are there at the 60th house. You told that your friends too, I am staying at the 60th house. So it has some door number. A 60th house has some door number. For suppose 20 b some 8 or 9. For suppose this is door. This is the address of this is the house addresses 20 b 89. This is the house address. House address. So he is coming to for suppose he call you, I'm coming to your house now, tell me your address. For suppose you tell me that address, so that address is the 60th house. So he is all the way coming to you and identify the, so he can process the 1, 2, 3, 4 and so on 59 and 60th houses. Then he coming to the 60th houses. Yeah. One another easy way is also there. Uh, to identify this one is very easy. This one is very easy. For suppose, yeah, I will tell you just a second. For suppose these houses, for suppose you are divided into the rows and columns, rows and columns, rows and columns, rows and columns, and columns, rows and columns. Here like this, rows and columns. These are the rows and columns. For suppose they can the entire so for suppose we are dividing this one into the rows and columns. So as sixth row, remember microprocessor or any other, first identify the row, then coming to the column. Remember, first identify the row and coming to the column. For suppose here, a sixth row is for where you are staying at 60. Or for suppose 67, for suppose 67th house you are staying at 67th house. For your here a brief explaining and clearly visibility purpose, I am considering this 67. For suppose 67 is directly coming to the sixth row. 1, 2, 3, 4, 5. Then sixth row is directly coming to the sixth row. This is column 1, 2, 3, 4, 5, 6, 7. These are the columns. This is 7. So directly coming to the sixth row here. Here coming to the sixth row. Yes. Coming to the sixth row. Then what is the column of that one? A seventh column. For suppose here they can stay here. This is very much easy to identify the address. A sixth row, a sixth row, okay, seventh column. For suppose sixth row, a 66 house, whatever it may be, 66 house. For suppose we are staying at 66 house. A sixth row, yes, sixth column. So this way, it is very much easy to identify the addresses. Okay, how how our houses are addressed, each and every house is a some specific address. For suppose how you can take that example as a house. Each and every house is a some specific address. This is the house address. So this house address has the, we are divided into the row and column. Microprocessor is also identify your address, or what is the address is here. This is the address. In this location we have the data. In this location we have the data, or nothing but I can also call it as information. Remember, this location we have the information. So microprocessor memory is also divided to the rows and, remember, rows and columns. Rows and columns. So for this is, for suppose we are identify this address. This address location we have the some memory. Memory. This address location we have the some memory. So how that memory addresses starts from, for suppose here the address is location starts from, for suppose 1. So nothing but rows and columns 1, nothing but at 0 0 0 0 0. This is the address. Now what is second address? 0 0 0 1 is the second address. What is third address? 0 0 1 0 is the second address. What is third one? 0 0 1 1 is the third one. What is fourth one? 0 1 0 0 is the fourth address. What is fifth one? 0 1 0 1 is the fourth. Then what is the sixth one? 0 1 1 0 is the sixth address, and so on. Up to how many address locations are there in the microprocessor? 1 MB memory locations are there. Then that is end at the 5Fs. Okay, so that entire total memory, it is somewhat difficulty to identify that total entire memory, 1 MB memory. Okay, for suppose you are consider the 1 MB memory into the rows and columns. So you are somewhat easy to identify that one, or somewhat easy to identify the microprocessor to this memory, RAM and ROM memory, physical memory, RAM and ROM, remember, and equally divided. So out of 1 MB, okay, out of 1 MB, 0.5 MB is RAM and another 0.5 MB is ROM. So to identify the easily to this our memory locations and all, so we are divided the entire memory into the segments. 16 segments. 16. How many? 16. Segment 1, segment 2, and so on. How many segments are there? 16 segments. So in the picture, they can only represent the two only for your easy understanding purpose. 16 segments. Out of the 16 segments, 4 are code segment memory, then 4 are extra segmented memory, then remaining 4 are data segment memory, then remaining 4 are stack segmented memory. Out of this 4 types of different types of segments. These are expressed used for the codes only. Nothing but microprocessor information. It stores at the microprocessor information. The programming information is stored at the code segments. The remaining 3 are used for the, can store the information and useful information. You can also call it as a data. For suppose you can store your name. For suppose a third year group 1, you can store at some location. That is stored at this extra segments or data segments. So, but that information is not stored at the code. For suppose you want to store the information like triple section A, where it is stored, whether it is stored at the extra segments or data segments, where it is stored, are code segments or stack segments. No, it is stored at the data segments. Whether the data segments is filled on that cases, extra segments you can also call it as, you can also use it as a data segment purposes. Okay, the code segment, so no information, so whether you are stored the information like your personal information or something information is not at all stored at the code segments. That name indicates that, you know, that name coded codes. Microprocessor codes information, nothing but move information or add information or like that information. When you add, when you on that micro it starts, it shows the some name. When you on the computer or some Microsoft, it shows the Microsoft, so it shows some another name, something like that, the predefined programming and all. So it's stored at the code segmented memory. So what is the memory size of each segment? Each segment memory size is 64 KB. Each segment memory size is 64 KB. So that how many segments here? 16 segments into the each segmented memory is 64 KB. That is equal to the 1 MB memory. This is the 1 MB memory. Yes, this one. Now the questions. How these segments are identify this memory? I mean microprocessor. How these segments are memories identify this microprocessor? Okay, how these segments are identified? These segments, how many segments are there? 16 segments. These 16 segments are identified by the four registers. What are the four registers? Code segment register, data segment register, extra segment register, and stack segment registers. These 16 segments are identified by the four registers: code segment register, data segment register, extra segment register, stack segment. Yes, these segments. This 16 out of, so in the diagram only they show the two segments, but it is the 16 segments. Out of, yes, that's why they indicates like this. This dots. This dots. Out of these 16 segments, the 16 segments are identified by these four registers, segment registers, code segment registers, data segment registers, extra segment register, stack segment registers. Out of 16 the segments, four, you know that four are code segments. These codes are identified the code segment register. Four code segmented memory identified by the code segment register. Again, four data segment are identified by the data segment registers. These four extra segment registers. Then again, four are the stack segment registers. So each and every register will identify the four segments. Like one code segment register is available to you, then one data segment register is available to you, one extra segment register is available to you, one stack register segment register is available to you. So one segment register is identified by four segmented memory locations. So this one data segment register is also identified by the four data segmented memories. One extra segment register is identified the four extra segmented memories. Then one stack segmented memory, then one stack segmented register is identified by the four segmented memory locations. Segmented register memory locations. Now see this. So segment will identify is the one segment register will identify the four segmented memory locations in this memory location. So that's why 4 into 4 is equal to the 16 segments. Is equal to the 16 segments. Okay. So out of these 16 segments, now see this. For suppose a microprocessor is able to identify the some code segments. So code segment register is identified by that four segment registers. Just wait for a second. Yes, these four segmented registers, now see this, is identify the 16 segmented memory. So where this segmented memory starts at, the segmented memory starts at 0, 0, 0 to the F, 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 H. Okay. Sorry, this is sorry 0, 0, 0, 0. Sorry. Okay. Yes. You can see this segmented memory here. Once again, see this segmented memories. So I do identify this. What is the segmented memory location starting at 0, 0, 0 to the H to the a 16-bit address? Remember, this is the 16-bit address at to the F 00H. F means a 15. 0 to the 15. There's nothing but the 16 segments. 16-bit address will identify the for suppose 00 for suppose 000 will identify the code segment 1, 0001 will identify the code segment 2, or 0010 will identify the code segment 3. So 0011 will identify the code segment 4, and so on. For suppose F000 will identify the stack segment 4 for suppose, and so on. So these are the 16-bit address. So this code segments, you know that you get the some clarity here. So this segmented address or segment register will identifies the, remember this point, a starting starting address of the, okay, segment memory only. Okay, starting address of the segmented memory. You understand? So so this segment address, a physical address is nothing but the segment address plus offset address. So the segment address will identify the, out of that 16 segments, only the starting address of these segments. Now see this. This is the one segment. This is the one segment. What is the each segment memory size is 64K. So the segment address will identify the starting address. Remember the starting address only. The starting address. Now see this one. No, this one. It identifies this one. Starting address of the segment only. Once it identifies the starting address, so after up to this ending address is this one. What is the size of that one? 64 KB. Who can identify the 64 KB addresses? Will identify the offset addresses. Nothing but is equal to the 2 power 16 is equal to the 64 KB. Yes. So offset address will identify the memory locations in that segments. Likewise, this segments. This segment addresses will identify the starting address of this segment. In this segments, remember in this segments, the address locations, the segmented address locations is identified by the offset addresses. Yes, this one is the offset address. Okay. Okay. So now see this, out of this 16 segments, as I said, this physical address, segment address plus offset address. The segment address will identify the starting address of the segments. What about this one? This offset address will identify the memory locations, in the segments. Remember, you should remember carefully. Segment address, the total physical address is divided into the segment address plus offset address. So segment addresses will identify the starting address. This is. So why it is only 60? So the what is the each and every segment memory is only 64 KB. Why it is 64 KB? Why it is only the 64 KB? Why it is restricted to the 64 KB? Because that offset address is a 16-bit. Nothing but 2 power 16 is equal to the 64 KB only. Because the memory locations, the address locations that will be identified in these segments is by offset addresses. Is by this offset address. But what is the offset addresses? Is easy. What is the bit size of the offset address? It is only 16 bits. So nothing but 2 power 16 is equal to 64K. So this way, so any microprocessor, nothing but 8086 microprocessor is working, is identify the total memory. So this segment address is so is only identifies the starting address. Remember, a starting address. This address will identify this starting address of that microprocessor. That another memory location. Like any code segments, a starting address of the segment. So in that that segmented memory locations will identify the memory locations in that segments. So this is the this is, you can call it as a non-overlapped segment. There is one another case is also there, that is the overlapped and I mean the another case is also the overlapping. What is overlapping means here? So before ending of the any other segment, how this memory, how this segment is formed here? It is the one segment. This is the one segment. After completion of this segment, okay, a second segment is started. This is the another segment. After this, one another segment is started. For suppose here, this is the another one. For suppose this is the another one. Then after the another another one, this one, this one. So it is not overlap, nothing but so one segment is completed, then start at the second segment, and then this is complete, then start at the next segment. Then this is complete, then start at the next segment. But due to in some cases, before closing up the segmented the entire memory, another segment is started by combining these two. These two, then but this memory size is of 64 KB only. That will be clearly understand. So for suppose now see this. This is the code segment one. For suppose this is the code segment one registered size. So this is the another code segment 2 for suppose. And the normal working case, this is the code segment 2. This is the code segment. But but see this. So before closing up that second segment, there is a one another segment is added here. Is added here. Now see this. By combining these two, now see this. They are mentioning here. Now see this, erase this. No, see this. So nothing but this is the segment. You can easily understand here. This is segment one. This is another segment. So by combining any of the two, will start the or in between that start the another segment. Now see this, start the another segment. By combining these two also, first of again I can draw the segment one, next segment two. Different overlapping means anyway, it can be overlapping anyway. So by combining half it form the one other segment. This is 64 KB only, 64 KB only, 64 KB only, 64 kb only. This is also 64. This is also 64. By combining these two are 64 kb. Why? Offset address is also 16 bit only. So this is the overlapping. In some cases, so we can consider memory is overlapping. Overlapping means that we can so before closing up, before ending of the any segment, the another new segment is started. So now see this example. This is code segment 1. This is the code segment 2. Before closing up that one, which one is started? For suppose code segment 3 is started, or for suppose code segment 4 is started. So now see this before now see this memory. This is the 64 kb memory. This is 64 kb. This entire memory is the 64. Now okay, this entire is the 64. Now that's why they can mention here this total entire memory. This because this is overlapped here and overlapping is available. And overlapping. Which one is overlapped? Segment 1 and segment 2 is overlapped. Segment 1 and segment 2 is overlapped. So I can clearly draw the pictures. This is also possible. Overlapping segment memory is also possible. So even though we are overlapping, what is the each segment memory size? 64 KB. How many segments are there in overlapping case? Is also 16 segments. Yes. Okay, that is the case. So this we can treat it as a memory segmentation. Okay. Then another one is also there. We can go for the for series. Yes. Now we are completed this RAM and ROM. So okay, that now come to the interface. Now come to the interface. How you interface different devices like the RAM and ROM and the input output device to this microprocessor. Okay, how we will interface this? So this will be going to be you can call it as the pin type. You can call it as the a pin and a signal description. So in the next class, we are going to see this and interfacing nothing but the pin diagram of that. So this is the total entire microprocessor. How many pins of that microprocessor? A microprocessor is of only of 40 pins. By using this 40 pins only, you can connect the input output devices or RAM and ROM memory by using this only 40. So how we will utilize this 40 pins effectively? Because we have only 40 pins only. Okay, how we can use this same pins for multiple operations? Okay, how you can use this the same pins? So now see this 38 37 36 35 pins. You can use it multi-purposes. So yes, see this AD16 S3. So how you can use this same pins for multiple purposes? Because we have the less pins, but you can perform the more number of operations, or you can connect the more number of devices to this microprocessor. You need to working with pins as a multiplex lines. Multiplex means a same pin will work as a different purposes. How is it possible? How we can use this pins as a multiplex lines? Then what is the description of this? What is the meaning of RT? What is meaning of hold? Okay, hold. What is the meaning of HLD and hold acknowledgement? What is write operation? What is memory and input output operations? What is data transfer and receive? Okay, so what is arithmetic and what is ALE? Okay, so in the next class we are going to see this party pins, how you are going to utilize this party pins as a multiplex bidirectional pins, and we're going to discuss it. next class. So thank you for joining the video.